Okay, we're recording. Okay. Hi, Professor. So we are Group Two, and our topic is WebPerf, evaluating what-if scenarios for cloud-hosted web applications. Um, we have the authors Yirong Jiang, Lenim Ravidranath, Sunamnath, Ramen Govidam, and the presenters are Precious in Academy, and I have my colleague here, Nitesh, also presenting with me. So the topic WebPerf, evaluating what-if scenarios for cloud-hosted web applications. So the first slide is basically the motivation. So as we can see that we have most popular like web applications we see have complex cloud architectures with multiple tiers and interrelated components such as virtual machines, SQL, no SQL storage. We have file systems, we have communication queues, we have third-party services, and also load balancers. So this basically is an example of a complex web application whereby we have different of the services interrelated. And we know that it's not really uncommon for popular web applications to include tens of different types of off-the-shelf cloud resources. And cloud providers, like Microsoft Azure or Google Cloud or even Amazon Web Services, they offer multiple resources for computation, for storage, for analytics, for networking, and also for management. This is an example of the different services that a cloud could provide, and this is an example of Microsoft Azure. Um, as you can see, they provide security and management. Under security and management, you have these different services. You have compute, you have integration, you have web and mobile. There's just a whole lot of services that it can offer to developers. For example, Microsoft Azure offers 48 resource types in 10 different categories, and each of these resources is usually offered in multiple tiers and different price, offering with different prices, with different performance and isolation levels for a web server alone. And the next slide is basically going to show you like the different select pricing for an Amazon cognitive search. So this is the different pricing tiers for Amazon Cognitive Search. You have the free, you have the basic, you have standard. You have we actually have three different standards. We have high density. We also have storage optimized and another storage optimized. So these are like basically we have cloud services offering different a whole lot of different services and also offering different pricing tiers for each of those services. Now, what happens is that the developer is now really faced with what we call a combinatorial resource configuration choices in terms of the number of resource tiers, the degree of performance isolation across the tiers, the redundancy of these resources, and the geolocation of these resources. So, as a developer who is trying to deploy a web app in the cloud, often we really need to like determine how the changes to service tiers or runtime load may affect the user perceived page load time. And this is where WebPerf comes into play. But before going into the idea of what WebPerf is, we want to figure out why did they really create an idea like this? So the first thing is that the prior work has actually explored technique to track casual dependencies in async applications. But since modern web applications are written using the task async paradigm, prior work is limited in this aspect. And as a developer, what we can do is that we can try to figure out different what if scenarios based on cloud providers SLA, but they are qualitative and insufficient to predict quantitative performance. Even if the quantitative performance was really available, they would also need to translate it to the end-to-end latency, which will require, application logic and underlying concurrency, which is really inconvenient and complex for a developer. Also, developers could try to like use data-driven techniques that rely on applications historical performance on various configurations, but they could be slow and expensive and not suitable for first-time deployment. So this is a picture of a developer really trying to figure out with all these resources that are at my disposal, and this is a type of complex web application architecture I'm trying to build. How can I figure out the um, cost effective service, the cost effective pricing tier that matches that matches on my scenario or different scenarios that I'm looking for. So basically, as a developer, I'm looking to find the cost effective resource tier for my web project. And doing this alone by myself is really going to be hard and complex, like we've seen in the previous slide around the different challenges that the developer might face. So this is where WebPerf comes in. And the main idea basically is a tool that estimates the distribution of cloud side latency of a web request under hypothetical changes, which are called what if scenarios, to the cloud side configuration of web application. So the key idea behind WebPerf is to combine data-driven offline latency models of various cloud APIs with application logic abstracted as what we call a casual dependency of various compute and input and output calls to compute the total cloud latency of a given project. So how were they able to do this? They were able to do this in three different steps. So the team was able to develop techniques to track casualties in task async applications. The second step was, WebPerf uses a new algorithm that hierarchical involves distributions in a manner that is guided by the causal dependence. WebPerf formulates the measurement problem as an integer programming problem that decides how many measurements of various requests should be taken to optimize total modeling error. The cloud latency of an application really depends on two things: on the casual order in various computation and input and output calls, and the latency of each computation input and output call. So we have two different dependencies that this cloud latency of an application is dependent on. So we have the stable dependency and we have the application independent API dependency. So the casual dependencies of various computations and input and output calls of a request in an application remain stable over various what if scenarios that we consider. And the second one is the application independent API latency. The performance of individual input and output calls to many cloud or resources can be reliably modeled independently of an application logic, but it could also function as a function of various workloads and configuration parameters. So, going a little bit deeper into the stable dependency, what that means is talking about casual dependencies of various computation and input and output calls of a request in an application can remain stable over various what if scenarios. And what that means is basically, if we take an example of a request that accesses like a key value store, followed by accessing a blob store, it accesses them in the same casual order even when the key value store or the blob store is upgraded to a different tier. So it really doesn't change, it's still stable. And this allows WebPerf to compute casual dependency for a request once and use it for repeated what if analysis. Going a little bit deeper about the application independent API latency, the performance of individual input and output calls to many clouds and resources can be reliably modeled independently of application logic, but as functions of various workload and configuration parameters. For example, let's take the latency of a Redis cache lookup API, and what it does is really just not dependent on the application, but on its configuration, such as like geolocation and its resource tier. So this is basically the WebPerf architecture. So how does WebPerf work? So the first is that WebPerf's binary instrumenter automatically instruments the given web application. So it actually controls the web application. The request in the workload and then executed on the app, generating two pieces of information, which is called the first one, a dependency graph, which shows casual dependencies of various compute and input and output calls executed by the request. and the baseline latency of various compute and input and output calls for the initial configuration. WebPerf also uses what is called a profiler, and inside a profiler you also have a profile dictionary. Well, what a profiler does is that it builds offline latency distribution of various cloud APIs under various what if scenarios. The core of WebPerf is actually the what if engine, and in that what if engine we have the dependency graph, the baseline performance, and the predictor. So what is the what if engine really combines dependency graph, the baseline latency, and offline profiles to predict a distribution of cloud latency of given requests under what if scenarios. WebPerf can also combine its predicted cloud latency with network latencies and client-side latencies to produce a distribution of end-to-end latencies. But it's also important to note that WebPerf really, this paper is really focused on cloud latency and not on the client-side latency or the network latency. But WebPerf can be combined, with network latency and client-side latency to provide a distribution of end-to-end latency. Then we also look at the prediction algorithm that WebPerf has, and it uses casual dependence between various computations and input and output calls invoked by a request. As you can see in the next slide, we have an example of what if scenarios, right? So as a developer, I can create like a what if scenario of a resource X being deployed at the location Y. And an example could be the resource X could be a Redis cache or front end, and Y could be a country in Singapore. Um, we have a tier which is a location X is upgraded to location Y. So we can have like different what if scenarios based on location, based on tier, based on input size, based on the load, based on interference, and based on failure. But the goal of this really is just to as help the developer easily create scenarios, to figure out the cloud side latency of their web application. And latency basically means, how much time does the request spend in the cloud before it reaches the client. So evaluating what if scenarios. So the first thing is being able to build application independent and parameterized latency profiles of various API offline. The second one is basically computing the dependency graph of a given request and application specific baseline latency distribution of various tasks in the request. The third is predicting the cloud latency by combining the dependency graph, the baseline latencies, and latency profiles for the given what if scenarios. Okay, so so we're going to talk about application independent profiling. So WebPerf maintains a profile dictionary containing profiles which are statistical models of latency of different cloud APIs under various configurations and inputs. In the implementation, what happens is that profiles are modeled by non-parametric latency distributions and are stored as histograms. WebPerf uses two types of profiles, independent and parameterized, and this just means that they depend on workload parameters or not. So that's what it means. So we have two types of profiles that WebPerf uses, independent. It doesn't depend on a workload parameter, whereby parameterized means that it's dependent on a workload parameter. So independent profile mode, we're talking about workload independent profiles. So independent profile model APIs whose performance do not depend on application or workloads, but may depend on configuration. So to profile an API for a specific cloud resource, let's take the cloud resource R, for example, which is a Redis cache. WebPerf repeatedly calls the API until it gets a good enough latency distribution. And then WebPerf's profiler now builds upon this profile for each API using different configuration of R, using different configuration of input parameters of the API, of different configuration of the system load, and etc. as well as at different times incrementally to capture temporal variabilities. Now, the next one we're talking about is the parameterized profiles. The performance of a small number of cloud APIs depend on workloads. WebPerf builds multiple profiles for each of these APIs, parameterized by relevant workload parameters. WebPerf allows developers to provide workload hints based on which it chooses the right profile for an API, and WebPerf now exposes to developers a list of APIs for which workload hints can be provided. So I'm going to hand it over to my colleague Nitesh to talk about the remaining slides.
Thank you, Precious. Uh, so I'll take over from here. So we'll start with what if engine. So as Precious mentioned in the previous slide, uh, in the diagram that there was a what if engine in which there was a dependency graph and baseline latency. So what exactly it does? So it actually predicts cloud latency under a given what if scenario. It takes an input profiles of a various APIs from different web applications, the dependency graph and the baseline latency of that task. And given the dependency graph, WebPerf estimates the latency of those tasks, that is the node first, that is the API, then combine that task latency distribution to estimate the total latency distribution of the request. Uh, so, uh, so what exactly is the challenges with the what if engines? So these are three challenges which is faced by the WebPerf what if engine. That is the profile selection. What in WebPerf uses the node, that is the API called in the node, which is not affected by the what if scenario. WebPerf uses the API baseline profile as its estimated latency distribution over here. Second is the enforcing concurrency limits. So what happens in the cloud APIs have explicit and implicit concurrency limit that can change the access tiers across the tiers. So say example, web application has different level of tiers like say standard S1, S0, premium P1, P2, P3. So you can change from this tiers from different tiers, and there can be it will face the challenges while changing the tier because the latency actually differs when the tier changes, whatever has been given by the cloud provider. Third is the probabilistic estimation. So WebPerf combines the estimated latency distributions of all the tasks of the dependency graph to produce one distribution of total cloud latency. The algorithm works bottom up and is invoked with the end node of the dependency graph in it. Precious, can you change it? Yeah. So these are some of the WebPerf extensions. So as I talked about the cloud latency prediction, this is the algorithm used for the cloud latency prediction, and where you can see there is an input given as a dependency graph baseline latency. Then the function has been called, and hence it has been explained over here. If you can change the slide. So similarly, like WebPerf actually depends on these two things. That is, one is cloud latency prediction, and second is the end-to-end latency prediction. In the next slide, there is an algorithm for the end-to-end latency prediction. Over here, if you can see, this is the end-to-end latency prediction. Like it takes an input as the web page and the latency vector of all the objects. Then the function has been called, all, and similarly, it has been explained. It is a self-explanatory algorithm, which you can go through it. If you can change the slide. So what after this, we'll go through the implementation part, how exactly has been WebPerf implemented. And in the paper given, there was 6 scenarios taken in hand to implement the WebPerf in the different scenarios. So the author demonstrate the implementation many times, not just 1 or 2 times, but in the 6 different scenarios, and they ought to achieve what exactly they were looking for. So WebPerf actually has less than 7% of error in all of the following. So these are some of the scenarios. That is, the application is social firm, means a production ready Microsoft application like an Instagram where an user can create an account, join and share the post and everything. The Azure services used over there is blob storage, Redis cache, service bus. So wherever you will see the word social form, forum, that means that this application has been used in the scenarios which we'll talk about later. Then there is something called as smartstore.net, where an open source e-commerce solution that includes all essential features to easily create and complete online shopping website, where mainly the services used is SQL for its database capabilities. Then there is a Contoso Ads, which is a advertisement website in which there is the services used is blob storage, queue, SQL. So the services which we have used in all of these applications are mainly blob storage, Redis cache, service bus, then the queue and the SQL. So these are five of the applications in which the WebPerf solution has been tested. So we'll move to the scenario one uh, in the next slide. So over here, if you can see, what if the Redis cache is upgraded from the original standard C0 tier to standard C2 tier? So what happens when the tier changes in the application? Say if you take the Azure web application, if you change the tier from standard to premium, you will obviously have a less latency over the application when you change the tier to the higher grades. But when you change it to the lower grades, the latency increases. So that is what has been shown over here. The result shows that upgrading the Redis from C0 to C2 changes the cloud latency and hence simply uses the baseline performance of the C0 tier as a prediction for the new tier, which can be inaccurate when you change the tier. But WebFerv actually has a very accurate, that is a median, average, and maximum relative errors, which is 0.8, 2.7, and 18.3% respectively. So you can see in the graph over here as the tier changes, the latency changes and the error over there as well changes. So we'll move to the scenario two. So what if the front end of the social forum is replicated to two locations? So there can be an enterprise solutions wherein like there are different users in different countries. So that it is not necessarily that the application has been deployed in one single location. So it is across the globe. So say for example over here they have taken the location as US East and the Asia East. So the backend would remain in the US West, but the applications will be performing in those area of the locations on the two different locations. So we configured the WebPerf profile dictionary with the latency modules for the social forum backend API in this scenario where front end and back end are deployed in the same data center. The modules were then added to the distribution between backend and new front end location that is over here, that is the US East. Uh, this helped them avoiding the profiling latency modules for all possible combinations of the front end and the back end locations. Over here, you can see the median, mean, and the maximum relative errors are less than 4%, 2%, and 15% respectively. Similarly, there is a scenario 3, 4, 5, and 6, which we'll go through in the next slides. So over here, it is only about the read and write data size of the X from the blob storage. So blob storage can be used for the static websites, storing everything. So over there, the read and writes of the hits which we are getting has been captured. The latency over here, if you can see, the median errors of all the values are less than 9%. Similarly, in the scenario 4, what if other collated application interfere with the social forum? So there can be other applications in the enterprise world which will be communicating through your web application. So Microsoft Azure does not guarantee performance isolation for the free tiers. So in all the application, there is something called as free tier or a basic tier per se. So they deployed it in the free tier and let other collated application create CPU pressure and see the load that is from 10% till the 80%. And while performing under the WebPerf, the median relative errors was less than 9% over there as well in the scenario 4. Then in the scenario 5, what if the end users concurrently load social forum web page? So these are all the different scenarios for the testing of the application performance, and the web performance for the errors has been taken care of in these all the six scenarios. Over here, the prediction errors was less than 10% and end-to-end median prediction error was 8%. So what happens over here is, say like a user continuously load loaded a web loads a web page uh, in every second. So in the back end, the load actually increases. So over here, like deploying the WebPerf, the relative error was less than 10% and less than 8% respectively. In the scenario 6, what if a replicated front end fails? So it is a good practice on a security point of view that replication should be there on your cloud platform, whether it is a VM as a form of backup or a DR. There should always be a replication. So for this scenario, we replicated the social forums front end on two web servers and place them behind a load balancer to see exactly what happens if one fails. So all the loads actually transfers to the other web server. That is the uh, baseline scenario or the optimum scenario, how the web application should perform in such conditions. Then we use the WebPerf to predict cloud latency if one of the web servers dies. So in such scenario, all the median relative prediction error was less than 9%. So if you see all the six scenarios, the error is less than 9, 4, or 5% only. So we can say that WebPerf was somewhat able to decrease down the errors while deploying it in your ecosystem. Then if you can move to the next slide, please. Yeah, so these are the median error predictions. If you can see, all we have taken all the six scenarios, that is Contoso ad, social forum, email subscriber, and their median errors have been shown in this graph. Then we'll talk about some of the, if you can change the slide.
Yes.
Yeah. Yep. So everything has their drawbacks. So WebPerf also have some of the drawbacks. WebPerf is accurate when dependency graphs are small and latency profiles are less variable and mostly application independent. These are some of the drawbacks. That is dependency graph complexity. The more input and output nodes in the dependency graph, the more potential prediction errors can be occurred in the WebPerf scenario. Then the profile variability. If the profile variabilities actually manifest the prediction errors. In all the apps evaluated, only social forum baseline profile was the least variability, which helped WebPerf generate a better predictions, which is shown in this paper given to us. Application independence of profiles, latency of queries to medium or large SQL table changes as TS changes, and hence using the baseline latency as estimates results in the large errors. And also there are some of the other things which you can add it to it. That is, there is something called as application insights in Microsoft Azure, which you can use for the logging of your web applications. So this that can also be a healthy practice for the enterprise developers to taken care of, that there should be application insights for all the web applications deployed, so that there would be logs generated, and based on that logs you can actually reduce or you can change the tiers according uh, to the hits and the latency, and have your latency control down. So I believe, and this is the summary, what exactly we have been gone through the paper. What exactly is the WebPer? That is an automated web app instrumentation tool that captures both browser objects and front-end cloud processing dependencies in a probabilistic framework, predicting web app cloud latency and end-to-end latency in six different scenarios, as we explained in the slides above. Six real websites were used in this evaluation. WebPerf achieves a median prediction error of less than 7%. I believe we are done over here. Thank you.
Thank you.